at these 5 objectives in this video. Please make sure you read sections 3.3 and 3.4 in chapter 3 and sections 12.6 and 12.7. There's something to do here. Put this in your notes and then put those in your notes. And let's go, monkey and cat. Okay, so matter. What can we do with matter when we're classifying it? Well, there's really a breakdown we can look at. You can classify matter into 2 main categories. It could be a pure substance where all particles are identical. Right? That's what a pure substance is. Every part of a pure substance is the same as every other part. Or there's mixtures where each part has unique identity. Right? So those are 2 main categories of matter, mixtures and pure substances. Now, pure substances, we've been talking about the elements on the periodic table. Elements are pure substance, and so every part of an element is exactly the same as every other part. Compounds are also pure substances. There's 2 different kinds of elements, and each time those bond together, they make a unique set of properties. Okay, so they're different from elements, but these compounds can be chemically broken down into elements. But each compound has its own identity, own properties, and every part of a compound is the same. Mixtures. There are homogeneous mixtures and heterogeneous mixtures. In a homogeneous mixture, each part has its own identity, but it's so well mixed. It's really well mixed, and so it looks like it's uniform. Heterogeneous mixture is not so well mixed, so each part that keeps its identity, you can actually see the different parts. Okay. So when we classify matter, we can look at these different things to help us describe it. So atoms are individual parts that make up all matter. Most elements are made up of atoms. Okay? Sometimes those atoms are individual. Molecules are 2 or more atoms bonded together. So atoms can be individual, or when they're bonded together, they're molecules. So these are molecules because it's 2 atoms. But these are the same atoms, so this is also an element. Okay. But it's 2 of the same atoms bonded together. Fluorine bonded to fluorine and chlorine bonded to fluorine. Chlorine. Okay. But these are also molecules too because it represents one kind of atom chemically bonded to another kind of atom. Okay. So a molecule involves chemical bond, whereas atoms don't involve being bonded to another atom. A pure substance, either a compound or an element, is pure. Okay. A mixture is each part has its own identity. But they're mixed together physically and not chemically. Okay. Compound is a chemical bond. A molecule has a chemical bond. So what's the difference between a molecule and a compound? Well, a compound has to have 2 different kinds of atoms. At least 2 atoms. 2 kinds of atoms. Whereas a molecule just has to have 2 atoms bonded together. Okay. So then there's 2 kinds of mixtures. Okay. A homogeneous mixture is well mixed, and a heterogeneous mixture is not so well mixed. You can see the parts. Okay. So matter can be classified. So if I looked at all this together, it'd be a mixture, and then it's evenly distributed, so it's pretty well mixed, so it's homogeneous. Okay. All right. So make sure to get these pieces of information down in your notes so that you have some definitions. But what makes up pure substances? Okay. The 3 kinds of smallest particles we talk about that make up pure substances are atoms, molecules, and formula units. Okay. So an atom is the smallest smallest unit of matter that has properties of a substance. Okay. An element's smallest part could be an atom. And then some elements chemically bond their atoms so they exist as molecules. What are molecules? The key to a molecule is it has to be 2 or more atoms, and it has to have a covalent bond. So it could be the same atoms, which makes an element, or it could be 2 different atoms, which makes a compound. So molecules are the smallest unit of many covalently bonded compounds, and then they can also be 2 atoms of the same element bonded together. A formula unit is when atoms turn into ions and then bond together. Okay. So Here's a slide to help us think of separating the difference between molecules, atoms, or formulation units, or elements or compounds. Okay, so this is an atom. This is a molecule. You can see there's chemical bonds. This is also a molecule. All right, but what makes these two different? They're both molecules. This is an element because all of the atoms are the same. This is a compound because you have different kinds of atoms, 3 different kinds of atoms chemically bonded to make that molecule. This is a formula unit because these particles are ions and they're repeated over and over and over. So it's a formula unit. And this is also a compound because they're different kinds of ions. Okay, pure substance or mixture. Every particle the same, boom, pure substance. Mixture of stuff that's not chemically bonded, boom, mixture. Okay, pure substance or mixture. This is, so we have to look at the physical properties of some substances. So physical properties used to separate mixtures, but you can't separate a compound using physical properties. Okay, cannot separate a compound physically. You have to do a chemical reaction to separate a compound. Okay, so salt water, boom. So we got salt particles and we got water particles mixed together. Salt stays salty, water stays watery, so this is a mixture. Okay. Mixture because each piece keeps its own. And it's also homogeneous because you can't see the salt from the water. It all looks the same. Okay? But we know there's salty salt in there and there's watery water in there, which each keeps their own identity. And we can separate them by boiling off the water, which is a physical change. Table salt has a chemical formula, NaCl, so it's a compound. So that's pure. Every part of table salt is NaCl all over and over again. Water, H2O, compound. So a compound has to have a chemical formula to describe it. Okay, oxygen, element. Okay. And oxygen is really O2, but it's O bonded to O, so it's an element. Okay, homogeneous or heterogeneous? Okay. If you say that's homogeneous and that's heterogeneous, make sure you can tell me why in class. All right, so what the heck is this all bonding stuff about? So why do atoms bond? They bond to be more stable. Stability happens when the valence shell is full, so the outer shell is full. So we look at fluorine here, we got 2, 3, 4, 5, 6, 7, 8, 9 total electrons. But if you notice, this outer shell has 7 valence electrons. Is 7 a stable number? No. So what fluorine's going to want to do is fill that outer shell. It could do that 2 ways. One way to do it is to hook up with another fluorine, and they can share these outer electrons so that they count for fluorine over here, 1, 2, 3, 4, 5, 6, 7, 8, and they count for fluorine over here, 1, 2, 3, 4, 5, 6, 7, 8. So by sharing valence electrons, atoms can fill their outer shell, sharing valence electrons. That's called a covalent bond. Covalent bond. Okay. What else can they do? Well, here's sodium with its 1 outer electron. Here's chlorine with its 7 outer electrons. If sodium transfers its outer electron to chlorine, then now sodium's outer shell is empty, which makes its inner shell stable. And chlorine's outer shell is full. They make ions, and then they make an ionic. They form ions and then make an ionic bond. So there are 2 major bonds we're going to be talking about, but this unit we're going to focus on covalent. All right, so covalent bonds, sharing electrons. Look at those gerbils sharing a carrot. That's so cute. What kind of elements are going to share electrons? Non-metals form covalent bonds. Okay. Now, sometimes we call the covalent bonds we're talking about as directional because the valence electrons that are shared between the 2 atoms and can't move around freely. They share to fill an octet, or and the shared electrons count for each atom. So here's a compound, NH3, that forms by sharing electrons. So how can we represent these molecules that form from covalent bonds? We do something called electron dot diagrams. Electron dot diagrams help us picture what the atoms are doing with their valence electrons. We can represent molecules and ions and atoms. All right, so step 1, find the atom involved on the periodic table and write the symbol. Let's start with nitrogen. Okay, it's on the periodic table, has 5 valence electrons. How do I know? It's in group 5 on the periodic table. So then I put those electrons as dots around this symbol. So I put 1, 2, 3, 4, 5. All right. And so this is the dot structure for nitrogen. And you pretend it's like in a box, and then you put one electron around each side of the box until you have to double up. Okay. All right. So here are some loose dot structures for other representative elements. This is one valence electron, one valence electron. So notice all of those have one dot in their dot structure. 2A, two valence electrons, two dots. Now, could I do this? Yeah, that's fine too. Okay. All right. So one thing that you can tell from an element in its dot structure is how many bonds it can form by counting the single dots. How many bonds can they make? Count the single dots. So hydrogen. Hydrogen can make one bond because it has one single dot. Fluorine can make one bond because here's fluorine. It has one single dot, so it can make one bond. Nitrogen can make, oh, this is what we did on the other page, 1, 2, 3 bonds because it has 3 single dots. That helps us decide when they start to bond with other atoms what they're going to do. Okay, so once you have more than one atom, you arrange the atom so that the one that makes the most bonds is in the middle. And then start bonding and make sure atoms have the same number of electrons that makes them stable. Okay, oh look, here's some molecules or ions. So we'll start with CH4. Here's carbon's dot structure, and here's hydrogen's dot structure. So which one can make the most bonds? Carbon, so I put it in the middle. And I know I have 4 hydrogens, so I'll line them up around that atom because I know they got a bond. And I'll put the one dot from hydrogen in. Now, anytime you have 2 dots, you erase in between atoms, replace with a bond because a line means a bond. Okay, and a bond means 2 electrons. So, erase. Okay, they're not erasing right now. So, I erased and replaced. And so then I have carbon, and it has 2, 4, 6, 8 around it, so carbon's stable. Hydrogen only needs 2 electrons to be stable because it's small like helium. Okay, NH3. So N has 4, this is its dot structure. Hydrogen's dot structure is that, so I know N goes in the middle. But this +1 sign means lost an electron. All right, so let's lose an electron. Go away, go away. All right, and now let's put in our hydrogens. Hydrogen, 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 hydrogen. Single dot for hydrogen. And then erase and replace all of the bonding pairs, those are called bonding pairs, with the line. And the line means 2 electrons. All right, since this has a charge overall, we put it in brackets, and we put the charge on the outside. PCl5. All right, there's phosphorus. All right, 1, 2, 3, 4, 5. Cl, 1, 2, 3, 4, 5, 6, 7. 7 valence electrons, but it can make 1 bond. So if we're looking at phosphorus, we're going, wait, phosphorus needs to spread out those electrons that we could put chlorines all the way around. And then share, share, and then share. We're going to share that electron. And then we erase and replace all of the lines, all of the pairs being shared to make bonds. All right, we'll save the rest of these for question. Okay. Now, notice not all bonds are single. Okay. So what happens if you get to a point where you're out of electrons but you have an unstable atom? You can multiple bond. So all we've been doing so far are single bonds. 2 electrons is a single bond. 4 electrons is a double bond. So these are single. And then double bond is right there. So what does a double bond mean? It means there's, this line means 2 electrons, that line means 2 electrons. So there's 4 electrons being shared by the 2 atoms. It's stronger than a single bond because it's more sharing. It's like more glue holding them together. And it's shorter than a single bond because these atoms can get closer together when they're sharing more electrons. All right, so double bond. Boom, there's another one. Boom, there's another one. Triple bond. Whoa, you're kidding. 3 pairs of electrons is 6 electrons, stronger than a single bond, shorter than single and double bonds. And so because all those electrons are being shared between those 2 atoms, and they're getting pulled in closer. Okay, here's some more dot structures. So we start with O, we have 1, 2, 3, 4, 5, 6. We have another O, 1, 2, 3, 4, 5, 6. Okay, I got that from the periodic table. Make a bond, erase and replace. 1, 2, 3, 4, 5, 6, 7 for that oxygen, not stable, needs 8. This one's same, not stable. So because I've used up all my electrons and I don't have stable elements, I have to erase those two and share those as well. And now 2, 4, 6, 8, this oxygen is stable. 2, 4, 6, 8, that oxygen is stable. And I only have 2, 4, 6, 8, 10, 12 total electrons. Okay, I'm going to go to this one. Nitrogen brings in 5 valence electrons. Oxygen brings in 6 valence electrons. Times 3 is 18. And then this negative means plus 1 more. So we got 19 plus 5 is 24 valence electrons. I'm going to put N in the middle because it can make 3 bonds. And I'm going to bond it to oxygen. Okay. And then I'll put in the rest of the valence electrons for those atoms. All right. So I do have 1 extra electron to add in, so I'll put it there. And now I'm looking, going stable, stable, not stable, not stable. Okay. So one thing that this molecule can do is take the 2 electrons on oxygen, single ones, pair those up. But then look at this, oxygen is still not stable. So we can take that pair on nitrogen and double bond it on that side. Okay, and then this is a -1 charge. Okay, so double bonds only happen when you run out of electrons and you need to make things stable. But wait, that one we just drew, why couldn't we draw it like this? Well, the truth is we can. This is just as good as that dot structure I just drew. But wait, what if we put the double bond down here? Oh my goodness. You're not going to believe this, but this is just as good as that other one. But what about the first one I drew, where the double bond was over here? So what these are called are resonance structures of each other. There are 2 or more dot structures that are equally valid to describe the same molecule NO3 negative. So resonance structures don't happen all the time, but they help us explain the dot structure of this ion, and they're just as good as each other. That's what resonance structures are. Okay, last but not least, structural formulas and molecular formulas. If you're looking at these, you can see the structure of each of these molecules, right? Because you can see how they're connected. So a structural formula shows you how the atoms are arranged. Molecular formula just counts atoms. So molecular formula would be C2, because there's 2 carbons, H, 1, 2, 3, 4, O2, because there's 2 oxygen. So molecular counts atoms, structural shows how they're bonded. So this is structural, see how they're bonded, but molecular we count C2H6. So that's molecular counts. Oh, look, we can match them up. So here's the structural, molecular, structural, molecular, structural, molecular, structural, molecular. All right, so give molecular formulas. We can do that one in class to practice. All right, so to review, elements and compounds are pure substances. Mixtures are physical blends of elements, compounds, and other mixtures. Compounds are chemically bonded atoms of different elements. All right, we're going to look at ionic, covalent, metallic bonds. Elements can be made of atoms. Dot structures need happy atoms. Okay, and remember I told you to read these books? Look at this monkey still waiting to go. Actually, he's like, woo, fun. Woo, fun. Okay, so do this stuff and this stuff. All right, peace out.